let me introduce our last speaker of the forum. He's Justin Kay, CTO and co-founder of the Ai.Fish LLC company located, I think, in Chicago, the US. I want to thank him again for his availability and on this time. That what time is in Chicago right now is
5 a.m.
Okay, sorry and thank you,
No
Justin. He's going to present the talk entitled "Opportunities and Challenges in Deploying AI Technologies for Fisheries Monitoring." So, Justin, please go ahead.
Okay, great. Can you see those slides?
Yeah.
Okay. So thanks for having me. I'm excited to be here. So my name is Justin Kay. I'm the CTO of Ai.Fish. We're a startup actually based in Hawaii, although I'm currently in Chicago. We're focused on AI and computer vision challenges in fisheries and marine conservation. One of our main focuses the last few years has been analysis of onboard monitoring data from longline vessels using computer vision. So excited to share some of our results.
Sorry, Justin, we are not hearing you. Okay.
Oh.
It changed. We can hear you properly.
Let's see. Is this any better?
Yeah. Thank you.
Okay, no problem. Let me know if it cuts out again. I might have to switch my microphone. So our primary focus has been electronic monitoring video from longline tuna boats in the Pacific Ocean. These systems collect video and sensor data in combination with existing human observer programs. They offer a great way to scale up monitoring, but at the cost of generating a massive amount of video data. Often they're
Sorry, Justin, it's happening
24/7.
again. It's happening again. We can hear you clearly.
Okay, how about now?
Much better. Sorry,
Much
sorry
better.
for interrupting you.
Okay. Okay, sorry about that. So as many of you are aware, these systems generate a very large amount of video data. And as these programs scale up, so does the amount of video data requiring review by people on land. So in order to help electronic monitoring really get to widespread adoption, we need a way to speed this process up. And computer vision provides an opportunity to do that by automating away some of the more tedious tasks. As you all are aware, computer vision has really exponentially advanced over the last 10 years. So if we can harness this, we can really allow monitoring to scale and importantly allow expert data reviewers to focus on the most challenging parts of the data and try to automate away some of the more tedious parts. The challenge here is that these modern algorithms are very data hungry. It's known that there's kind of a power law relationship between model performance and data set size. So if you want to cut your error rates in half, you often need to double your data set size. And while these big open data sets like ImageNet and OpenImages have pushed forward performance on a number of computer vision tasks, there's very limited fisheries imagery here. And so a challenge becomes, how do you get a computer vision program off the ground for electronic monitoring? And so one project we've been fortunate to be involved with is this initiative led by the Nature Conservancy called FishNet AI. It's an open source data set of onboard electronic monitoring imagery for fish detection and species classification. Right now it's around 100,000 images and it's growing. So if you haven't checked it out, please do. It's great and we want to keep improving it and expand it to fisheries outside of the Pacific and different gear types. So the data set has allowed us to do some experiments to examine kind of the unique challenges of electronic monitoring data and look into how existing computer vision models do and how their performance transfers to electronic monitoring. And what we found is that the EM data is quite challenging compared to common benchmarks like ImageNet and COCO. We took some popular off-the-shelf deep learning models and compared their performance, and it's significantly lower off the shelf due to challenges such as harsh weather and poor lighting, water on the lens, and, different reasons that the fish become occluded. The data is sourced uniformly from real-world conditions, so the species distribution kind of matches what fishermen are seeing in real life. So there's a long tail distribution where the number of tuna images, because this is a tuna fishery, is exponentially larger than the number of non-tuna species. And so we found that models do significantly worse on these rare classes as well. I think this won't be surprising to anybody that's worked with this kind of computer vision data before. But this has obvious implications for important conservation goals like detecting protected species interactions, where obtaining training data is very hard, and we naturally are not going to have very many examples. We also found that it's hard for these models to generalize, so they do pretty well on vessels that have some data in the training set, but then they struggle to generalize to new vessels for which there's no training data. And this has implications as EM programs scale, and we're going to need ways to get good performance on vessels that are just entering an EM program and have recently installed systems and no data yet. And so I think this points us toward what I think is kind of my main point of this presentation, which is that harnessing the computer vision to improve electronic monitoring has two parallel work streams. One of which in the long term is kind of the fundamental computer vision research challenges that are very interconnected with fisheries data. And these have been brought up in previous presentations today, so it's exciting to see all the research that's being done here in few-shot learning for the rare classes. Object tracking is a hugely challenging problem. The systems on board longline vessels are often, the cameras are often not positioned in a place that's really conducive to easy tracking. There's not really like a linear motion guarantee or anything like that, and the fish become occluded quite often. These are super important challenges. Long term, they're going to make a huge impact, progress in these areas. But what I see as the other work stream is what can we do right now in the short term, given that we have sort of imperfect models. Can they still improve things for us out in the real world right now? And how can we use them as components of systems which are designed to improve monitoring and conservation? And so that was kind of the motivating question behind a project that we worked on last year with the National Fish and Wildlife Foundation, in which we built a computer vision backend for electronic monitoring data processing using open source models, and looked at ways we could incorporate model output into user interfaces to speed up workflows of people reviewing electronic monitoring data. The system that we built uses object detection and species classification to filter down the large quantities of raw video data coming off the boats. So it attempts to filter out the uneventful portions and segment down the data into important clips that contain catch events, which the user can then quickly cycle between and view the most important parts of the data stream. So the AI annotates these catch events and presents them to the reviewer in a streamlined workflow where they can watch the video in a way that mimics existing workflows, but we'll also see the observations that the computer vision model has made. Each of these catch events has some associated metadata, which is best filled in by the fisheries experts. What's the condition of the catch? Was it kept or discarded? Was there damage to the animal? Eventually, computer vision may be able to also automate some of these tasks, but for now, we leave it to the reviewer, and the main focus is reducing the time spent scrubbing through empty video. And I think an important thing here is that we recognize and indicate in some way that the AI is probably noisy. We want this to be a human-in-the-loop system that increases efficiency, and so we require the user to either confirm or reject the AI annotations. And of course, there's the ability to add in anything that the algorithm may have missed. So I think if we can think of AI algorithms in this fashion as assistants to reviewers rather than complete replacements, we can start to see operational benefits in programs almost immediately. The side effect of deploying systems that we know are noisy is that we need a way to fact check them. So this is a complicated question that I don't necessarily have the answer to, but we need to figure out a way to put into place systems for auditing the algorithm predictions, feeding back corrections to its predictions in order to kind of iteratively improve the models in an active learning way that's also been brought up today, be able to perform quality control, and we need to come up with a way to quantify the error of the algorithms and figure out first what's an acceptable margin of error, and then how can we incorporate this known error into management and regulatory decisions. So it's not easy to deploy these solutions. It's messy, but with some thought and planning, I think it can really help scale up monitoring and contribute to more sustainable fishing practices. And so one other opportunity that I'll bring up, which is related to this short-term work stream, is a recent project that we worked on with Archipelago Marine Research. They're an electronic monitoring service provider in British Columbia. We built a machine learning system for identifying sets and hulls using just onboard sensor data. And so for anyone that's not familiar with the terminology, a set is when you're letting out the gear, and a hull is when you're reeling it back in. And so the sensor data includes things like vessel speed and heading. There's a rotation sensor on the drum that is letting out the gear, and then there's a hydraulic pressure sensor when you're bringing the gear back in. And so identifying sets and hulls from the sensor stream is a task that involves some pattern recognition that people do really well. So we figured it was a great fit for machine learning, and it was. We're able to achieve prediction accuracy of over 95% with a model that is lightweight enough to be incorporated into an existing piece of video review software. So right now, Archipelago is working on incorporating this into their production software called EMFF. We're super excited to see that deployed, so keep an eye out. And with that, I'll wrap up. Thanks for having me, and I'm looking forward to the discussion after this.
SICAPTOR, monitorización electrónica para una mejor gestión.